Alrighty, problem number one, simple pendulum, bob attached. We have a velocity of 0.4 meters per second there, period of 1.3 seconds, max velocity of 0.4 seconds. Looking for the amplitude of the motion in degrees and the maximum tangential acceleration of the bob. We know that theta is equal to, or theta max times sine omega t plus this guy. Take the derivative of that, we get theta dot is equal to theta m times omega n cosine plus that. We know that our omega max is equal to theta dot max, which is equal to theta m times omega n, and now we know that our v max is equal to length times omega dot m, which is equal to our length times omega m times theta m. So theta m is equal to Vm divided by length times omega n. Vmax is 0.4 meters per second. And omega n is equal to square root of gravity divided by length. And we know our omega n is equal to 2 pi divided by our period, and that gives us 4.83 radians per second. Now that we have that, we can find our length, plug in 4.83 meters per second, divide gravity by that, and we get 0.42 meters. And then we know our omega m is going to be equal to 11.29 degrees because we have our V max, our length, and our omega n, and we get our max is 11.29 degrees. Then we can sub in some of these guys over here to our omega or theta m. Omega n's cancel and such, but trying to remember what I did here. Oh, we know that length is equal to g divided by omega n squared. That doesn't really matter. Then we can't take the derivative of this guy, or just that guy, actually, a little simpler. Again, we get theta double dot, and we're assuming a maximum sine this equals 1, and that would be when theta double dot is equal to max. So we get theta double dot m is equal to negative omega m, or theta m times omega n squared. We know that tangent acceleration is equal to length times theta double dot, and so we can sub this guy into that guy to get our maximum tangential acceleration. We have all those values and such, and we get maximum tangential acceleration of 1.93 meters per second squared. 2 springs for this guy. We have one set in series, one set in parallel, both with K1 and K2 on both. For the ones in series, we know 1 over Ka is equal to 1 over K1 plus 1 over K2. It gives us K2 plus K1 divided by K1 times K2, but you have to take the inverse for Ka, and we get K1 times K2 divided by K1 plus K2. Then in parallel, you can just add them together, and we know omega n is equal to square root of K divided by m. We know that Ta, or the period is equal to 2 pi divided by angular velocity. And then we can sub in for angular velocity for both equations, and we can get a K value for both sets. So that is Ka, that would be Kb, and this is Ka. And we can divide those by each other, and in the end we can get period values squared. Tb squared divided by Ta squared is equal to 0.16. And we also can divide Ka divided by Kb, and we have values here. We have Ka and Kb. and we can set those equal to 0.16, and then we can get a quadratic equation here. We can say K2 is a constant, and that would allow us to set everything, or find square roots for K1. So use quadratic formula, set in our values. We get K1, well then we can divide by K2 later on. Remember, constant, and we get 4.25 divided by 2 plus or minus 1.875, and with the max, K1 divided by K2 is equal to 4. Problem number 3, we have a heavy piece of machinery, 3,500 kgs, causing a 40 millimeter deflection on the second floor of a building with an unbalanced rotor. Assuming the deflection of the floor is proportional to the load it supports, determine the equivalent spring constant of the floor system. So pretty much the force of the spring, we can find that we know the force of the spring is equal to K delta. And then we're looking for the speed and RPMs the rotating machinery should avoid to not coincide with the natural frequency of the floor machinery system. And so we know it's not going up and down, so force of the spring minus weight is equal to 0, or force of spring is equal to the weight. And so K delta is equal to mg, so we get K is equal to mg divided by delta, and we get K is equal to 858,375 newtons per meter. And then we know the natural frequency, omega n is equal to the square root of K divided by m. We know that natural frequency is equal to omega n divided by 2 pi. And so we have all these values that we can set in. We had a natural frequency of 2.49 hertz, which we know 1 hertz is 1 revolution per 1 second. And so if we times that by 60 seconds per minute, we can get revolutions per minute. And that is 149 revolutions per minute. Number 4, I'm a little confused by this. I'll explain in my free body diagrams, but we have 2 springs pulling. We're currently in equilibrium, and we pull things this way by 0.012 meters. We're looking for the period of vibration of the system and the magnitude of the maximum velocity of bar AB. So here we have the delta or x value that it's moved. And then we have the kx, or the force of the spring here, force of the spring there, because if you move this way, this spring is going to want to push you that way back to equilibrium, and this spring is going to want to push you or pull you towards itself to equilibrium. And then, so we have that, but then we're also accelerating this big ol' cylinder, so that is going to be pulling it back with an internal force. So on the cylinder, there should be a force going that way, and then if we're no slipping and rotating that way, because if you look here, if velocity is that way, as I have here, or let's just say here, velocity is that way, that means angular velocity is that way, and if we are moving that way, that means friction is also going that way. So a little confusing here, because the solutions had it as friction going the opposite way, both in the math and free body diagram, but I'm not sure that's right. We also know that x is equal to r theta, and then so theta dot is equal to x dot divided by r, and theta double dot is equal to x double dot divided by r. And then free body diagram, so we have x double dot is acceleration, and civil forces is equal to the 2 spring forces minus the force pulling it that way. And then we have, for the cylinder, x double dot is equal to the force minus the friction, F that, and then we have the moment about the origin is going to be equal to I alpha is equal to the sum of the moments, which is just the friction, because it's the origin. This is the only thing that's not going through the origin. So that is equal to 1/2 mr squared. Theta double dot is equal to friction times the radius. So we can divide both sides by r, and we get friction is equal to 1/2 mr theta double dot. And then we have F is equal to mx double dot plus 1/2 mr theta double dot. And we know theta double dot is equal to x double dot divided by r. So we get mx double dot plus 1/2 mx double dot is equal to 3/2 mx double dot equals F. And then we have mx double dot is equal to 2kx minus 1/2 mx double dot. Do some algebra and rearranging, and we get that m plus 3/2 m x times x double dot plus 2kx is equal to 0. And we know that over here, this k, if that was equal to 1 and such as k, that omega n, or natural squared, is equal to that k. We're looking for that omega n. So we can divide by that m plus 3/2 m, and then we can set that equal to that omega n, and omega n squared. We can get an omega n value of 27.74 radians per second. We know the period is equal to 2 pi divided by omega n. So we get period is equal to 0.227 seconds. And then we know that Vmax is equal to absolute value of 0.1, or of the max distance, I guess, times omega n, which ends up being 0.333 meters per second. And then number 5, uniform disk radius 0.12 meters, welded at its center to 2 elastic rods of equal length with fixed ends at A and B, knowing the disk rotates through an angle, or 8-degree angle, with 500 millinewton meter couple applied to the disk. It oscillates a period of 1.3 seconds. When the couple is removed, determine the mass of the disk and the period of vibration if one of the rods is removed. We have a torque spring constant with the rods because they like to return to equilibrium and such. And so further you go, the more torque that is applied to the disk. The torque is equal to the k theta. So we get k is equal to t, or torque divided by theta. So we have a torque value and we have a theta value in degrees. Can convert from degrees to radians by multiplying the degree value by 2 pi divided by 360. And then we get 3.58 Newton meters per radian. Then we have a moment about the origin. Was negative k theta is equal to I alpha. And so after some rearranging, I alpha plus k theta is equal to 0. Now the natural wn squared is equal to ki. And we can sub that into our frequency equation. And in this equation our period equation, and that allows us to find our moment of inertia after some algebra. So moment is 0.1533. We know that the moment of a disk is equal to 1/2 mr squared, and so we can use that. The only thing we don't know is the mass, so we can solve for the mass, and that is equal to 21.29 kilograms. And then for part B, if one of the rods is removed, we're assuming that the torque value is dropped in half. So K2 is equal to K divided by 2. So that is equal to 3.58 divided by 2, which is 1.79 Newton meters per radian. So our period number 2 is going to be equal to 2 pi, or the same thing as this. But yeah, just rearranged a little bit. And we know all values, so we can just plug them in, and we get T2 is equal to 1.84 seconds. Then that's all I've got. A little time crunch at the end and didn't fully get through the rest of the homework.